our universe, its beginnings, and potentially its ending, and maybe the fact that we're not the only universe around, and that there may be, in fact, a whole series called the multiverse. One of the key things that's happened recently is we've had just some amazing scientific data that's come available. First was the Higgs. And you might say, well, what does the Higgs have to do with astronomy or cosmology? Well, actually, it could potentially, it has a lot to do with it. So we're going to talk about that later. But probably the main event that's happened, it just happened this month. The Planck satellite, European Space Agency, was measuring the cosmic microwave background radiation, and they produced on February 5th 38 papers of the average length of about 40 pages came out. And so what I'm going to do is give you some idea what's in those, but and it was drinking from a fire hose to somehow digest all of this. But there's several of the other books that are very interesting. I mentioned here Many Worlds in One, so I would talk about this. That'll be there. Alan Guth, who was the first to propose inflation. Lawrence Krauss, A Universe from Nothing. And then this book, which is an excellent book about the Higgs. And and there was a conference and some of the data that came out from a conference that just occurred. So it's a lot of stuff that's happening in real time. So what we're going to do today is we're going to, you don't try to read this. If some of them are a little too busy like this one, but what we're going to do today is I'm going to give you a little background on the Big Bang cosmology as we sort of known it up until the Planck time. Planck meaning this recent data. It doesn't change things remarkably, but we're going to talk about some of the features of the Big Bang model, but there's things that it doesn't address, something called the horizon block problem and the flatness problem. We'll be talking about that as well. Cosmic inflation, which actually has been proposed to solve these problems. We're going to talk about an interesting idea as to how maybe all of this happened. I mean, the Big Bang is one thing, but what caused the Big Bang? And so that's, we're going to talk a little bit about that. Then we're going to talk about the cosmic microwave background radiation. This is amazing stuff. This stuff is, you're embedded in it. It's all around us. It's in the, and this has information that goes back to times potentially all the way back to 10 to the minus 34 seconds after the beginning. And so and it's all around us. It's radiation that's everywhere. So we'll talk about that. Then we'll talk about Higgs. And in fact, it's becoming clear that cosmology and particle physics are quite interconnected. And for example, this is just a little diagram of the temperature of the universe as a function of time. And this was like 1 minute after the Big Bang. This is 500,000 years, and here we are out here. But during this time, and one key event, we'll talk about inflation. I think most of you probably have heard about this before, but it's a time when the universe went from nothing to quite a large size in 10 to the minus 35 seconds. But after that, then the standard Big Bang model takes over, and we have all the various forces that were initially all unified at super high temperatures. And for example, the Higgs, the whole business about the Higgs was breaking apart what's called the weak force and the electromagnetic force. And the weak force is what governs decay of nuclei. Anyway, but all of this, while this is happening during this period, the universe is lots going on, and so we'll talk about that. And then another aspect is that inflation has become so much of it solves so many things. In fact, it's been referred to as, well, we don't have any direct evidence, but it solves so many problems that it's too good not to be true. And so one of the consequences, though, if you buy inflation, is that you almost have to accept the fact that there are multiple universes. And we'll talk about why. And then there's another question is, well, you know, why do we exist? Why is everything so just perfect for us? How did it happen? Well, if there were an infinite number of universes, you don't have to, because we're just one of many. And one of a possibility. So getting right into it, so where did we, and what we're trying to, what I'm trying to illustrate here is just some of the experiments that went on starting in the 90s and up through the 2000s. And there were several key things that happened. One was the supernova cosmology project and the high Z. This was a study using the Hubble telescope looking at galaxies that are way far away, 500 million light years away, and measuring their speed, how fast they're moving. And lo and behold, they found out they expected to see the universe begin to collapse. That Hubble's law says that things recede proportional to the distance away. So if something is 10 times further away, it's receding 10 times faster. But they expected to see that reverse, that as you go way out, things maybe aren't receding that fast, that it's getting smaller. Well, that's exactly what they didn't find. They found just the opposite, that the universe is going faster than the Hubble constant, Hubble's law. And that's a puzzle because there's no force that was known to man. The longest range force we know of is called gravity, and it's attractive, not repulsive. So this was a major surprise. And that's where dark energy comes in. That is dark because no one knows what it is, but it seems to be a repulsive force. And so that piece of data, then all the measurements of the cosmic microwave background, we'll get into that. But if you plot these things, this is essentially, this is dark energy on this axis, and this is the total amount of matter in the universe. And it's all normalized, so it's to a certain constant, and I won't get into what that is, but here's all the data. So there's data from the supernova project, there's data from the cosmic microwave background, and then there's data from the clusters of galaxies, essentially measuring the mass of the universe. And amazingly enough, they're all very consistent, and they give you a value. And what they show is that this dark energy is 70% of everything in the universe. When you throw in all mass and matter and all forms of energy, electromagnetic, every type of matter or energy there is, 70% is this stuff we don't know anything about. And then to make it even worse, the actual amount of the total amount of matter comes out to be about 0.3. So 0.7 is this, 0.3 is the matter. But mostly of that matter, most of it's called dark matter, which isn't, and the matter we know about is like 4% of the total. So 95% of everything is something that's dark, and we don't know anything about. We're learning a little bit about dark matter. And we also learned something about the age of the universe. You put all this together in Einstein's using something called the Friedmann equation, which comes from Einstein's general theory of relativity. You do all that, you get an age of the universe of 13.7 billion years. So anyway, that's just a little bit of background on the history of, and this is all new stuff. 20 years, well, let's see, it's 2015. So 25 years ago, no one knew any of this stuff, and we now know just a tremendous amount. Okay, and so the conclusions of the quote-unquote standard Big Bang model, which basically is that our universe is, well, okay, now let me show you this. This is a plot, this is time here. 0 is now, -1 is 13.7 billion years ago. So 1 is 13.7 billion years in the future. And this is the size of the universe. So it went to where it is now from essentially nothing. But then you'll notice, you see what's happening here is it's curving up and it's accelerating. So there's this dark energy that's in that this repulsive force is causing the universe to expand even faster than it is right now. And so the net of that is that what people expected to have happen was the universe eventually collapse. looks like it's just not going to happen. So right now it looks like the universe is going to expand forever. And the universe is also at this, at something called the critical density, which is an interesting concept. But what it means is at this particular density, the light isn't bent. Light is bent around massive objects, but if you just take the universe as a whole, it's not really that densely populated, and light travels in a straight line. And that's a very unusual situation. It's like a rocket taking off from a planet, a random rocket on a random planet, and all of a sudden that rocket going into orbit, just having the right amount of energy to not escape or fall back. And so the fact that the universe is at this critical density is really strange, and there's no good reason for it unless something made it happen. We'll get into that. And so then this discovery of dark, these are Nobel Prize winning stuff, and this is and there are several people won Nobel Prizes for this. So all of this stuff is really right at the cutting edge of what's going on. So in spite of how good the Big Bang model is, it's got some problems. One of which is that the universe, light isn't bent, and light travels in straight lines. It's called a flat, and I remember that confuses a lot of people. What do you mean the universe is flat? Well, it's just astronomers' way of saying light isn't bent. The universe is not flat; it's three-dimensional, and so as I mentioned, that's a very it doesn't happen all by itself. Something made it happen. So that's a mystery that the model does not explain. The second one is this cosmic microwave background radiation coming at us from all directions. Looks like it was once at one spot, and but it's coming back. It's coming from the right, it's coming from the left, coming from the top, coming from the bottom. It's coming at us from all different directions, and it looks like it once was thermalized. It once was in thermal equilibrium, which means that once had to be at the same place. But how can it be at the same place when it's the stuff that's 13.7 billion years it took to come from the right, 13.7 billion years to come from the left, yet you're saying it was always at one place? Big mystery. Okay, so that's another thing that the model didn't explain. And another issue is structure in the universe. After the Big Bang, the universe was perfectly uniform, but obviously it isn't anymore. We have galaxies and planets and stars. So something came in. What caused this structure? And so in 1984, so this is going back a few years now, Alan Guth proposed inflation to solve all these problems, and it does. So some of this is going to get a little heavy. I'll try to recoup it and get you to the bottom line, but I gave this talk to a bunch of scientists, and so I'm doing this. So there's something called the Higgs Field, the Higgs boson. You've all heard about that. Well, this is real. We now measured it. But the Higgs field is a constant field that pervades the universe, and as you know, it gives mass to the particles like electrons and protons traveling through this field is what gives those particles their mass. And so Guth decided that what we need is something like a Higgs field to solve this problem of inflation. And what is the nature? Why is it special? Well, what it is this is just a diagram. This is a field in X and in Y, and this is the potential field. And what the Higgs field is that when the fields are zero, it's sitting here at a high potential, and so the characteristic of that is that it's called a false vacuum, and it has a very interesting property. And the interesting property is, so imagine you have this little plunger here, and you have some of this Higgs field false vacuum inside here. And now imagine pulling on the plunger, and all of a sudden, if you do, and if it's constant energy density, you've just created some more energy. It's now bigger. The energy has gone up. So how could that happen? Well, you had to work against it. Your hand was pulling on this thing, and it did work. Well, how can if it was normal vacuum or even positive vacuum, it would be pushing and would help. But we've actually added energy in here, so there had to be work done by pulling at it. What does that mean? this was in suction. This false vacuum, property of something at a constant energy density is in suction, negative pressure. And negative pressure is exactly what we wanted, what you need here to explain inflation. And so, Guth proposed this state of this false vacuum filled with a Higgs-like field at a constant energy density, and that's and if you solve a Friedmann's equation for a constant energy density negative repulsive force, you get an exponential growth of the universe. So that's why what Guth did. He proposed this Higgs, and at the time, this Higgs field was known. It had never been seen. Higgs boson hadn't been found in 1984, but it was making big news. And so people accepted the fact, well, okay, so this Higgs field, we'll buy this, we know about it, it solves some problems for us. Well, maybe it caused this inflation. So that's where Guth was thinking how all of this, we've come a long way on that track. At some point we decided that, well, it actually can't be the Higgs field. But now we're thinking, well, now that we found the Higgs boson, maybe it is. And so there's a lot of interesting stuff going on. So one of the interesting things, though, about this, getting back to inflation itself, one of the interesting things about it is that it's causing the universe to, during inflation, negative pressure, negative gravity. So the universe, you work it out, it expands 25 orders of magnitude or more in 10 to the minus 34 seconds. Now, it's this staggering amount. 25 orders of magnitude, it's hard to even imagine what that is, but that's a lot. This is way faster than the speed of light. And you can say, well, how can that happen? Well, the way it happens is that Einstein's special theory of relativity says nothing goes faster than the speed of light, but space can go faster than the speed of light. Just the expansion of space can be at any speed. Objects can't go fast, but space can expand. And that's, so what Guth was proposing, and you worked out that the universe is, during this period of inflation, expanded this tremendous amount. Well, so here we have this Higgs field, which has constant energy density, and now it's just expanded 25 orders of magnitude. And if you want to, you want to do 25 orders, take a million times a million times a million times a million times a million. That's 25 orders of magnitude. So all of a sudden, the universe is filled with this incredible energy. But the amazing thing about this is that the universe has zero energy. So how can it have expanded by 10 to the 75th cube of the size, and yet we're at zero energy? The reason is that in the process of expanding, there's something else called the gravity. And in the gravitational field, as the universe is expanding and we are accumulating all of this Higgs energy, the gravitational energy is negative and completely matches it. So the net energy is zero. And so this state goes on, but it does go on real long because this false vacuum state is metastable, and the Higgs field rolls down to a lower energy state, and the growth stages end. So what happens is once the inflation period ends, all of this energy in the Higgs field gets converted into particles and radiation, and that's the beginning of the standard Big Bang model. And Guth referred to this as the ultimate free lunch. So you end up with a universe created from virtually nothing that expands by this huge amount, has zero net energy, and yet we have all those particles and everything that eventually becomes us. And anyway, so he calls it the ultimate free lunch. So what else does inflation solve for us? Well, I mentioned that this question about light traveling in a straight line, and it's not a natural thing in space. The consequence of solving general relativity says space wants to be bent, either bent one way or bent the other, hyperbolically or parabolically. It doesn't want to be flat, and it's unstable. Like if you can imagine a pin sitting on its tip, just sitting there, and somehow not falling over, unstable. Well, how can that happen? Well, what happens is inflation expands the universe by such a degree from 10 centimeters to 10 to the 48th meters in this. So imagine a balloon. So something, a universe which has some curvature. So the balloon analogy, it maybe helps understand it. And imagine blowing this balloon up by this. At that point, the universe looks this balloon looks very flat. And even though there's a minor, so this is in a sense, the mathematics work out, it shows this rigorously, but this is easier to understand, that it's like something with curvature blowing up and becoming essentially flat. So that's how inflation solves the flatness problem. It just drives the universe to such a state of flatness that light travels in a straight line. And the other problem about the horizon, so here we have, so how does inflation deal with that? This is the issue where light is coming at us from opposite directions, 13.7 billion years from the right, 13.7 billion years from the left, and it once was in one place. Well, how does that happen? Well, it happens because it was once in one place. It's in thermal equilibrium, so all the photons are at the same energy, and so now inflation comes along and expands this thing tremendously. So now, where these 2 points, if you were sitting here, you would see point A and point B. Now inflation expands things so much that point A, but this going way faster than the speed of light, the universe itself, you can only see at any given time, the amount of, you can only see from like 13.7 billion years, and as time goes on, you see, you see a little bit more. But but now point A and B are we can't see them anymore. They're way outside outside our horizon, which is limited by the speed of light. But eventually, time drags on, and the universe is still expanding, but not nearly as fast anymore. And points A and B finally, with enough time that the light that was from point A and point B are now reaching us again. And that's why the light is so uniform from 2 different directions. So that's how inflation solves the horizon problem. Then the other problem, if I remember, was, well, where did this, okay, so I'm going to step back a bit. Okay, how did this magical false vacuum, who made that? I mean, that's essentially the beginning of the Big Bang, but where did that come from? Okay, so this is an interesting question. It gets a little philosophical, but it turns out, well, then and Vilenkin even answers a question, which is, well, maybe the universe didn't have to have a beginning. Maybe it's been expanding from infinity. It's always been expanding. And he shows, I'm not going to walk you through this, but he shows that if you follow the logic here, it amounts to something having to go faster than the speed of light, and it doesn't happen. So he proves that, and it's a very, well, okay, it's so simple, let me just explain it. He said, imagine an expanding universe. Universe is expanding, you've got observers, and every observer throughout the universe, the further away you are, the observer is going faster. This is Hubble. And so if you're twice as far, he's going twice as fast. So imagine a spaceship just sort of cruising along in space, passing these observers. The further observer is going to see the spaceship going slower than the previous guy because the universe is expanding faster. And so, okay, so that's fine. Flip it around. Let's go back in time. Then the observers are going to see this guy going faster, because remember, he was going slower when he was going out, but if you go back in time, he's not, the observers earlier are going to see him go faster. Eventually, he's going to hit the speed of light before, and at that point, he can't go any faster. So the assumption that the universe could have been expanding forever can't be true, because this guy's going to be, you'll have to have him going faster than the speed of light. So it's a contradiction, and it can't happen. So that's why the universe has to have had a beginning. It wasn't always expanding from some infinite time. Infinity is a tough problem to beat. Okay, come back to the question. Well, all right, it had a beginning. Did it have, what caused this, let's say this false vacuum state? How could it have happened? Well, Vilenkin in the same book, Many Worlds in One, proposes, he makes the minimum set of assumptions that you can make to explain this, and it doesn't violate physics. So what he's assuming is there's nothing, there's no space, there's no time, there's nothing, but physics exists. So the mind exists, but no matter, no space, no time. Well, if you postulate then a closed spherical universe with zero energy, turns out a spherical universe that is closed, like if you keep going, you come back to the same point, has by its nature is zero, has zero total energy. It's the potential energy it just balances the energy associated with movement of things, and so it has zero net energy. Imagine it's filled with some of this false vacuum, maybe a little bit of ordinary matter, and because it has zero energy, the uncertainty principle. If the uncertainty principle says if you try to locate a particle or very tightly, its speed will be unknown. If you try to locate the speed part, well, the same thing happens with energy. If you have something with a finite amount of energy, it won't exist there very long. And but if it has zero energy, it can last forever. It can be there forever. And so the uncertainty principle is violated. So all of this, imagine zero energy, no, and so this can. And one of the amazing things about quantum mechanics is things don't have to be caused by things. Things happen all by themselves. There doesn't have to be causality associated with quantum mechanics. Now, normally, all of this could in fact have come out of nothing. And so now imagine, well, in most of the cases, these little blips of small spherical universes would not last very long. They would collapse and recombine. But it turns out, if you look at it, there's still a vanishingly non-zero, even with a universe going almost to zero size, this false universe, this fluctuation, there's a non-zero probability of quantum tunneling through the barrier of that Higgs field. This is what I showed you this potential barrier. So you're sitting here in zero field, and there's this little barrier here. So, but there's a finite probability that this particle will get over the top and then enter this inflation period. And so the probability can be vanishingly small, but as long as it's not zero, and you have an infinite amount of time for this to happen, it can happen. And so that's Milankovitch's proposal for how the original universe, or the Big Bang, happened. It happened out of nothing. Now, there are other people who have different ideas about this. The only thing you can say for sure is that you can't actually test this. This is non-testable theory. But the interesting thing is it doesn't violate any laws, any physics. So it's a possibility. Okay, so here we have this false vacuum appearing out of nothing, and then it explains. The universe expands. This inflation happens, and as I say, the inflation itself is almost too good not to be true because of all the problems it solves. And so that's how things began. And what happens is, during the inflation period, you're actually you get over the hump and you're sliding down, and eventually you reach the end where the energy is now zero at a finite field. So you're left with a finite field, but you're down to a zero energy, and this is the end of inflation, and normal Big Bang occurs. One of the reasons that they said that the Higgs field probably couldn't do this is that the Higgs field, the nature of the problem it was solving, which is giving mass to particles, requires that this is a fairly steep slope. But it turns out when you look at the details, this inflation potential has to have a slow roll. It has to take a while, even though it has to take a while for this inflation, so that you create enough matter so that you drive the universe to be flat, and that the fundamental particles, that there's enough energy in the inflated universe so that when it ends, it turns into energy that's necessary for our universe to occur. And so this is called a slow roll. And the Higgs field can't be a slow roll. So people, all right, it's not the Higgs, it's a Higgs field that's like it, but it has zero, it has a constant energy density, and then it rolls down to having a finite field value. So it's similar, but not the same. Okay, we'll come back to that. And so here's inflation. We solved many problems with it, but it also solves the question about where does the structure of the universe. So here's a sort of a cartoon of what's happened. So you have cosmic inflation occurring for this 10 to the for the first 10 to minus 34 seconds. Then particles form. All that physics that I showed you earlier all happens. You split apart the weak force, the strong force. All of this happens, and then eventually you reach the time where something called recombination occurs, and that's here. What that is, before the end of inflation, or the end of this period, the end of inflation was very quick, but during this period here, you can't see back beyond this point. And what's happened here is, we'll talk some more about that, but what happens here is that the universe's temperature has dropped small enough that light and matter, light isn't scattered anymore. Anyway, that's what we'll talk about that. And then after that, you start forming particles and eventually galaxies and what have you. So how did this structure come from? Well, the origin of the universe, or the structure of the universe is critical because I said before, during the inflation period, it would have presumably been exactly uniform. But the way inflation solves the structure problem is that quantum fluctuations occur during the inflation, and some areas end inflation a little bit earlier than the other. So you have time here, and this is distance. And so some areas are ending inflation earlier than other areas, and the areas that are ending inflation later have higher density. So what you have is small regions that after this inflation period that are slightly higher in density than other areas. And so that's how this initial little bit of structure, non-uniformity occurs. It occurs during inflation. So then comes the cosmic microwave background radiation. So I mentioned that this is left over because after the universe has cooled down to 3,000 degrees, before that, light and matter were just scattered continuously. So you couldn't look back. Just like if you were looking up at a cloud bank, you can't see any further than the bottom of the clouds. Well, that's essentially what happens here. Because during the early universe, up to this recombination time, light is being scattered. You can't see back any further than that. And that occurred at 380,000 years after the Big Bang. So you had inflation, and then gradually the universe is expanding at a slower rate. Eventually it cools down, and atoms are formed. They're not electrons and protons. Atoms form. Light isn't scattered anymore. But you have this radiation that's left over, and that's the cosmic microwave radiation. And it's now, it once, at 380,000 years, it was about 3,000 degrees Kelvin. Now it's at 2.75 degrees Kelvin, but it's still there, and it's very uniform, but it's not 100% uniform. In fact, one of the first people who saw this radiation thought it was at Bell Labs, and they thought it was bird poop on their antenna, but they figured it out, it was real, and they went to Princeton, and the people there told them what it was. It's left over from the Big Bang, this radiation. And interestingly enough, they got a Nobel Prize for it. The guys who figured out what it was for didn't get anything. So Nobel physics favor the experimental way more than the theoretical, although this seems preposterous, but anyway, that's the way it is. But so here we have the cosmic radiation. It's all around us. And the amazing thing is that even though you can't see back any further than 380,000 years, if something affected the cosmic radiation, and if it's present in the cosmic radiation, you can study it and maybe learn something. And in fact, you can learn a lot. Okay, so let's talk about this structure. Remember I said different parts of the inflation ends, but not perfectly uniformly, so there's a little bit of clumpiness due to which area, what spots ended first or later. A little bit of clumpiness in matter. And turns out that little bit of clumpiness affects the light in interaction. So light and matter are really very tightly coupled during this during this period before the decoupling and atoms, light isn't scattered anymore. So light is slightly higher densities of matter affect the light, and it's because of the theory of relativity, and it's called the Sachs-Wolf effect. And I won't, that's all you really need to know. So regions of slightly higher density will cause the light to shift into longer wavelengths. Lower density will cause the light to shift into blue shift, which is into shorter wavelengths. So you'll have now this light which has slightly, which isn't uniform anymore. It's regions have longer wavelengths, other regions have slightly shorter wavelengths, all having to do with the fact that there was matter that it was interacting with wasn't uniform either. And so at the end of inflation, so there were these matter variations, but they also included light. They impacted the light, and this couple. So it turns out that since I mentioned light and matter were tightly coupled, they propagate through the universe at time about 70%. It's like a sound wave. So imagine a little blip of non-homogeneity initially, like throwing a pebble in a sand, and that wave from that propagates. So that's what's happening. Is this little bit of slightly light has changed its wavelength somewhat, and this little bit of higher density or lower density matter is like it starts out at the end of inflation, and then it just propagates outward. And the dark matter, interestingly enough, so there's also dark matter here too. But since the dark matter doesn't interact with light, it just stays fixed. So you have this blip in the middle, essentially right when at the end of inflation, and then this wave of matter and regular matter and light travel out like a wave, and they travel out all the way until in this period of decoupling, when light and matter aren't coupled anymore. And this is the point when the temperature drops low enough that the universe cools off, and we don't have this coupling. So light is now free to move unscattered. It turns so the actual, so here we have our first little blip, but there turns out there's many little blips, and this pattern exists now in cosmic microwave background radiation when it's released. So there are regions in the radiation that are slightly warmer and slightly cooler, and they propagate out through forever, and in fact we can still see it. And this just shows that. So you have this time. This is the non-homogeneity and time. So initially you get this blip. The dark matter stays place, and light that's also coupled to it. And then the coupled regular matter propagate out. And at the end of inflation, they have reached, and as I explained, they have reached the farthest distance. So if you had an initial blip and you had this matter and light coupling sound wave, at the end of inflation, the distance it went from when it started to it's the longest distance these inhomogeneities could have traveled. And this is the maximum spacing that any of these little variations in matter could have traveled. Turns out there's some other ones that wouldn't have had to travel, but nothing can travel any farther than that, because that time, that 380,000 years, sets the time, and so it can go, if something happened right away, it can go all the way out that way. So this distance is a yardstick great deal of information can come from that. And so what you have, this is the W map of the inhomogeneities in the cosmic radiation. And if you look up real close, you see these things. And so these inhomogeneities will propagate through time up till now. And these pairs of inhomogeneities, remember, they are still moving apart from each other. And the distance that these are now are a function of how the light, whether the light is bent or not. So imagine at the end of inflation, you have these little bits of inhomogeneity spaced apart from each other, and then now we're up to 13.7 billion years later. These light traveled through the universe all this time to get to us. Now, if the universe had curvature, so the light was bent, this distance would change. We can project the distance as if the light wasn't bent. That is, how fast can 13.7 billion years minus 380,000. That's the time. And if light wasn't bent, we can now tell you how big that yardstick between those two coupled inhomogeneities would be. But if it was bent, it would either be longer or smaller. So measuring these homogeneities provides a tremendous amount of information. Here's what you do when you're looking at this cosmic microwave background radiation. You sit in here and you're looking for essentially difference in wavelength, which translates to slightly difference in temperature, and that's what you have. These are in Kelvin. So what they do is they look for these pairs of inhomogeneities, and they see how far apart they are, and they look, and there's lots of them, but they see it, so they look for that, and what they found out is that for a scale, and this is the scale in the sky, degrees in the sky. For scales that are less than 0.6 of a degree, there's nothing. There's no blips that are related to each other. But all of a sudden, you get this big blip where you start. All of a sudden, you see these pairs of blips are related. You look all through all of this, and it's at the same space and sky. And this is this is the angular scale, and this is the temperature difference. And you get a blip because this corresponds exactly to that distance that the first particle, this inhomogeneity pair traveled up to the end of when light was decoupled. So that distance can still be seen in the sky now. And when they look at the cosmic microwave background, at 0.6 of a degree, they see a blip. And they also see some higher ones. And these correspond to shorter distances. But the longest distance that it could have, that these pairs could have gotten apart is associated with this first blip, and that's 0.6 of a degree. It turns out, magically, that is exactly the separation it would have been if light wasn't bent at all during all that time. It went straight at us, no curvature. And it turns out we learned some other things. They're by analyzing this data different ways, they can actually come up with how much dark energy, how much matter, and so you can learn an awful lot from measuring this cosmic radiation, which I think is just mind-boggling. That here it is, we're immersed in it, and yet we're getting this information about what was happening 13.7 billion years ago, and it's impregnated into that radiation. And the other amazing thing, and I've given parts of this talk before, so some of you will remember this. It turns out that actual spacing in the sky in distance is 480 million light years. So there was a study measuring the separation of galaxies, galaxy clusters, not galaxies, but galaxy clusters. Galaxy clusters are groups of galaxies that are gravitationally bound to each other. These are the largest structures in the universe. So by measuring the separation between these galaxy clusters, and so here's the cluster population, and this is the distance. And there isn't an awful lot going on. All of a sudden, at 480 million light years apart, there's a blip. There are more galaxy clusters that are separated by this same amount. This is the same amount that was represented by that spacing in the cosmic radiation. So the cosmic microwave radiation, the anisotropies in that, were the blueprint for all the structure in the universe. And you can see it here. I mean, it's that study, I forgot the name of the study. It was done it was done in between 2000 and 2010. Anyway, so that's pretty amazing. And so I mentioned earlier that discovery of the cosmic radiation, and it essentially at the time sealed the deal on the Big Bang, because it had to be there, and lo and behold, it was there. And there were some other things having to do with the amount of hydrogen, and helium that the Big Bang correctly. So essentially, it was a seal on the deal. But the structure in it hadn't been seen until 1990. And the first, so this was a big deal because people tried to see the structure in the cosmic microwave background radiation. This structure that I showed you already, but up until 1990, no one could see it. They couldn't measure that. From Earth, it looked perfectly uniform. The cosmic radiation, no blips, nothing different. But COBE was set up as a satellite, and in 1990, it reported back there are anisotropies. They're small. They're 1 part in 10 to the 100,000, 1 part in 100,000. It had never been observed. But that again was another big aha or big sigh of relief, because there had to be there, and lo and behold, they were there. Now, since then, there's been 2 more generations of satellites that have analyzed this cosmic radiation. One is called the WMAP, and the other is the Planck. And the Planck is the most recent one. Yeah, and as I say, it was critical that it be there because the structure that is in the universe now had to have been existing prior, during the inflation period and after, and it had to have affected the cosmic radiation. And in fact, that has happened, so it was a big deal. So this is the Planck data, and this is just and so these are all the color represents the temperature difference from uniformity. Red being hotter, blue being slightly colder. But these are in microkelvins, 10 to the minus 6 degrees. So these are very small differences. But the Planck satellite was much more sensitive than the WMAP, 2 parts per million versus 6 parts per million, so 3 times more sensitive in measuring these temperature differences. And they did it at about 9 frequencies instead of 5. And as I mentioned right at the start, on February 5th, several weeks ago, they released, I said more than that, 28 technical papers, 60 pages on the outset, on the average 40 pages. A lot. They also, it turns out this light, the cosmic radiation, when it was first released, was not polarized. It was perfectly uniform. But with one caveat, there was hope that maybe we would see some small unpolarized light, or polarized light, that came from gravitation waves, and I'll come back to that. But anyway, to first order, it was unpolarized. But after a certain amount of time, stars began to form. And once stars were there, now you had light that could take a hydrogen atom and make it, ionize it, and make it into a proton and an electron, rather than and now light is scattered again. Now the cosmic radiation is scattered now because the starlight is causing these ionized particles to happen and scatter off the CMB. And so what they've learned that in fact the first stars occurred at 540 million years after the Big Bang, essentially the end of inflation. Because the Big Bang, by the way, the bang in the Big Bang is inflation. That is what it is. It's this expansion of the universe by this huge amount. That's the bang of the Big Bang. Well, anyway, by studying the polarization that occurred because of these first stars, they were able to figure out when the first stars were formed, and also they were able to map the amount of matter, how the matter varied in the universe. But this is heavy stuff, getting this data. Here's the final piece of data. But the cosmic radiation is coming through the Milky Way, and there's light at that same frequency at 2.7 degrees Kelvin generated by the Milky Way. And that all has to be sucked out of the data that they're measuring in the satellite. And so like this, for example, is the microwave emission from the Milky Way right here, this big mess. And the red is thermal radiation from dust, yellow is carbon monoxide gas, blue is something called synchrotron radiation. All of this had to be accurately measured by Planck and then subtracted out of the actual data to get to these, to see the actual cosmic microwave radiation and not the. So it's contaminated by radiation that exists in the Milky Way.
Mike?
Yeah.
Could we take a couple minute break?
Sure.
Because I think I have to come out
Oh, okay.
in there.
Do you want me to help you?
Yeah.
What is the picture? What is the cloudy picture of the
Yeah.
light?
Oh, I see. Yeah, this is This is the magnetic field in the Milky Way.
Oh, I see.
Yeah. And so that's a mess too. All of that has to be figured out and subtracted to get to the real data.
So Mike,
Yeah.
they're not measuring the actual temperature, they're measuring the,
Sorry, Mike, Sam.
You gotta leave. I understand. I'm sorry.
Thank you.
Well, I'm glad you were able to come, Joe.
Okay.
the,
Yeah, they're
it's from the size of the wavelength.
the wavelength. That's what. No. But it corresponds to a temperature difference too.
So just imagine that when every time they talk about temperature, I imagine a thermometer.
Yeah,
It's not-
no, it's they're measuring the fact that it's at 2.75 degrees Kelvin. You can translate the energy to a temperature, and so they are measuring differences in wavelength. And this data, they've been waiting. For all these years, they've been waiting. They've been using the WMAP polarization data, and just in this February, they released their own polarization data. And this is the mess that it looked like, because there's lots of polarized light coming in the Milky Way, and when they suck all of that out, they get to this. And so there are swirls here. That has to do with the direction of the polarization, and the color is the temperature. So they had to pull all that apart. They were able to measure, as I mentioned, because of the fact that the light is passing by these galaxy clusters, is bent slightly by the clusters, and it turns out they can figure out what the mass was, density throughout the universe by looking, by measuring the cosmic radiation and how it was deflected and they use that to correct. They use that to make an additional correction on the temperature data. And so this is the Planck data, and again, what this is a temperature variation between coupled parts of these anisotropes, these little blips. So this is the temperature variation that they're measuring between these blips, and this is size in the sky. There's something called a multipole, but in effect it corresponds to size. So this blip is 0.6 of a degree, and these are smaller. This is smaller, but you can immediately see the difference in the accuracy of the WMAP versus this. They're heading this thing out to 8 of these and multiples, and the model is able to predict to match the data dead nuts. And this is the polarization data, same thing. The model is able to, and what is the model based on? The model is based on parameters, a key set of 6 parameters. And the Planck data, and there's some of the ones that are more familiar to us, are the amount of normal matter. So normal matter went from 4.4% during WMAP to 4.9. The dark matter went up 26.5% from 24%, and the dark energy went down from 68.4, all adding up still to 1, which is the key. That meaning when it adds up to 1, it means that we're at this critical density and light isn't bent, and the data is entirely consistent with that. So that hasn't changed. WMAP was able to show that pretty accurately, and Planck's data is just that much more accurate. And there's small differences because their first data came out in 2013, and this is now 2 years later. The age of the universe was modified to 13.8 billion years, another from 13.7 from the Planck data. And these columns all correspond to different sets of data. So this is just the Planck temperature data. This is the Planck temperature data and the polarization data. And all of the accuracy, they can come up with these same numbers from the temperature data or the polarization data. And that's actually what this one is. This is one polar, and they're all very similar. And when you put them all together, they get this really super accuracy for these numbers. But there's more to. They're learning more than just these densities of matter. And one of the things they learned is the frequency spectra of these anisotropies was thought to be perfectly uniform, so that higher frequencies or lower frequencies appearing in the sky were exactly the same amplitude. Well, it turns out they aren't quite the same amplitude, and they're not scale invariant, which means that the amplitudes at higher frequencies drop off slightly. And when it's 1, it means so this is their polarization data, and they show that if the data where there is these fluctuations are uniform in frequency, and that's called at 1, doesn't fit the data nearly as well as it does when it's 0.96. And there's something else called the tensor to scalar ratio, which is the size of the polarization effect to this temperature effect. Tensor meaning anyway. Tensor means polarization in this context, and scalar means temperature variations. So what they do is they plot this. This is the tensor variation, and this is this scale invariance, and here's 1. But you can see the data, and all of these various curves are more further constraints on it. And when you take all the Planck data plus the baryonic acoustic, all other experiments too, you come up with this blue thing down here. So this says that the tensor ratio and this scale invariance occurs in this bound. So who cares? Well, what this determines is that you can figure out what the potential for the inflation field, and that's what's plotted on by these other things. And what is shown is that at this point, the potential drops off uniformly with space. And above here, it goes off quadratically or higher, and down here it's concave. It's dropping. So straight line, quadratic, concave. And so the data from Planck says we can't have anything beyond essentially no, just at linear power. It can't drop. It'll drop off linearly. The scalar potential. You have to go back and realize what I'm talking about. This is the potential of this Higgs-like field, and this is what I'm talking about. Is the slope that takes you from this flat part at the top down to 0 where inflation ends. It's that slope that is determined by this data. and it says it has to be concave. And it turns out that's good news for people who believe in inflation, because this favors slow roll inflation, which is necessary to explain the effects, that is the flattening of the universe, also the proper amount of particles that had to exist at the end of inflation. And so it couldn't come down that potential too fast, because if it did, it wouldn't have had enough time to do it. And so the inflation people have already said that it's got to be slow roll for it to happen. And the Planck data says yes, it's going to be slow roll. So the Planck data is really supporting inflation. It's not it's not the smoking gun. I'll get to the smoking gun in a minute. But it says that the shape of that potential is consistent with the Planck data. So that's also a big result. And so Planck supports inflation is what the bottom line is. Okay, so this is the smoking gun. Some of you may have paid attention to a big deal. This was in New York. This was in all the newspapers, all the magazines, not just technical, but everything. And this was a team that was called Bicep 2. They operated a telescope, a form of a telescope. They were looking at the cosmic microwave radiation at the South Pole, because they thought that there would be the least interference with the Milky Way down there. And they were right. This is actually the Planck data, and this is the area that the Bicep team was looking up through. So the blue means there's less noise, there's less Milky Way interference down there. Well, they came up and they claimed they had a 5 sigma result for seeing the primordial polarization. So what is that? It turns out when this cosmic inflation occurred, incredible growth over a very short period of time, Einstein's general relativity says there's going to be a gravitational wave caused by this huge change in matter and energy over this very short period, would have created a gravitational wave. It turns out a gravitational wave would have affected the cosmic microwave radiation. It would have polarized it in a particular way. And so these people were looking for that polarization, that particular type of polarization that would be consistent, that could only have come from inflation. So that's the smoking gun. Seeing a gravitational wave directly in the cosmic radiation of a particular type is the smoking gun. This is Nobel Prize winning stuff. They said they had it. That was last March. Well, unfortunately, they used they thought it was good, but they used some questionable data to take out the noise from the Milky Way. And actually, they took it from some of Planck data. What they did was pretty remarkable. It's hard to believe, but what they did was they took a graph that was in a presentation that one of the Planck team made. They took that graph and they analyzed the data on that graph, and they used that to take out the Milky Way interference. And they said they had done that, but they didn't. Initially, it wasn't clear where they got the data to do this, but it became clear later. And then all of it, then people started throwing stones. They said, "Well, you did this, and I can't believe it." And then on top of that, and then it was, as time has gone on, there's been little dribbles of data. The real Planck polarization data didn't come out until just this month, but the teams knew what was going on. Eventually, these two teams got together and they agreed that the size of the effect that they were seeing was comparable to the interference with the Milky Way, the interference from the Milky Way. And so, one of the fellows in the geology club who's actually has interacted with the Bicep team says, actually, it's not quite that bad. They still think there's a 1.5 sigma accuracy to it. They think they're still seeing it. But they both agree, that is, both the Planck team and the biceps team said it's no longer a smoking gun. I mean, it's not a slam dunk, but they still think it's there. Well, anyway, bicep 3 is going on now, which is they're going to measure the same. They're down at the South Pole. They're going to measure. They're going to measure it at different frequencies too. So they're hoping to get. So this is not. This story is not over, but this would be an amazing accomplishment to actually see a polarization wave, or the effect of a polarization wave that occurred in minus 34 seconds at the beginning of everything. So anyway, stay tuned. I'm only going to show, just look at this, and then I'll summarize this in a couple of words. They started looking at other forms of where the dark energy, could the dark energy be caused by? And they came up, and there's a couple of possibilities. One is that Einstein's general theory of relativity is wrong, and that's so modified gravity. Gravity isn't quite like Einstein said it was. That's one possibility. Another possibility is that if you remember, the repulsive force, what we call dark energy, is a repulsive force. It's somewhat like the same repulsive force we were talking about inflation, when inflation grew very fast, much weaker, but maybe it's caused by the same kind of field. Maybe it's caused by this constant energy density field. And if that's the case, it won't be constant forever. It'll drop off. So they started studying various types of how this, not inflation field, but how the dark energy field, if it came from a similar type of field, how it would have fit the data. And so they have different forms for that fall off. And this is the nominal data. But some of these things are allowed. So they're saying that and they call this quintessence, this type of dark energy, which is not constant, but is caused by a Higgs-like field. But it would be really a slow roller. I mean, it would be rolling down not in 10 to the, in 380,000 or 10 to the minus 34 seconds. It'd be rolling off in billions of years, 10s and 20s and 30s of billions of years. So, but it's a possibility. And anyway, they tested a couple of these things. The other thing they found out, they could actually, there was some discussion that maybe there are more than 3 neutrinos. They were able to show that there's only 3 neutrinos, and they have an upper bound on the mass of the neutrinos. So just a tremendous amount trove of information about the universe that can be dragged out of this data. Another interesting thing about the data is this. This was a 2013 Planck result. And what they found out then was that the temperature in one part of the, looking one direction, was different, and there was a real line between it. And some people in the literature, some people, journalists, call this the axis of evil. And then there was a cold spot too. And so this appeared in the 2013 Planck data. I didn't see it in you didn't see this in any of the recent ones, but it's not gone away. And all you have to do is go on to go in and Google axis of evil, and you'll see this. So people had looked at this, and they said, well, what is this could be? Well, maybe it's the result of two parallel universes colliding or interacting with each other. And the other possibilities, it's just wrong. It's data artifact. So anyway, lots of possibilities. It hasn't been ruled out what it is. I don't see it in any of the current data, but this discussion is still going on. And if you go on the internet and Google cold spot or axis of evil, you'll find all sorts of discussion on this topic. Okay, so we're getting close to the end of this, and I'll go quickly. But I'm coming back to the Higgs. So we talked about Higgs-like field. So Higgs field has been proposed to solve a problem about, essentially, I'll oversimplify it, that how particles get mass. And it's more complicated than that, but take it, for this purposes, we'll just say it that way. So it had been proposed in the 60s, And Steven Weinberg in '67 put it all together, and he was able to properly explain the splitting of the symmetry, as it's called, between the weak interaction and electromagnetism. Anyway, he put off, so the Higgs field, by the 80s, when inflation came up, the Higgs field was on reasonably firm ground. People, they hadn't seen the Higgs boson, but the field, the whole thing, fit the data very well. And hit, by the way, Weinberg, just to give you a feeling for the level of this, Weinberg got a Nobel Prize for that. So, and so, but one of the interesting things about the Higgs, and this is just coming out from very recent data when they finally measured the mass of the Higgs boson. It turns out they found out that in doing this, that we may be in a metastable universe. And so what this is the mass of the top quark, and this is the Higgs mass. And the Higgs mass is now, and when you look at it, it falls within these circles. But interestingly enough, this is a stable universe, this is a metastable, and this is unstable. Well, okay, so the data says we're not unstable, but it doesn't say we're stable either. In fact, we're somewhere in between. And what this infers is, what would it mean? Well, you're sitting here at a certain Higgs field, and but there's a lower energy solution to this, but there's a barrier in between. Well, that's what is called metastable, because if somehow this thing, the state of the universe went from this, the value of the Higgs field here to this value, everything would change. Because the Higgs determines the mass of simply, say, just the electron. If you change the Higgs field, you change the mass of the electron. If you change the mass of the electron, you change the size of the atom. If you change the size of the atom, chemistry is all different. So all the chemistry that we're familiar with in the universe is totally different. So, so what would happen is if somehow we went from one state of the Higgs field to another, a lower energy state, the universe would be totally different. You don't have to worry about it too much, because it would travel here at the speed of light. So it would be over before you even saw it. So, because nothing travels faster than the speed of light. So if there was a disturbance, if some part of the universe jumped this barrier and got to this lower, this different field, it would propagate through the universe at the speed of light. And maybe it's happened already. But people don't think so. But that's one of the interesting things that came out of finding the mass of the Higgs field, Higgs boson, was predicting this. But so this opens up all sorts of other questions, and one of them is, why, if during inflation the Higgs field was there, and if during this inflation period, if the Higgs was here, there's tremendous energy, why didn't it get to this lower energy field? Or why shouldn't it? So people are asking that question. Then the other question is, well, is there any way the Higgs field, I call it Higgs-like, maybe it is the same field as caused inflation. But I told you about the slow roll problem. But it turns out the theoreticians started looking at this, particularly since the boson Higgs was found. So we now know it's real. So you say, okay, I got this is real. Maybe I can somehow find a way to make it explain inflation. And the answer is you can if there is a coupling between the Higgs field and gravity. And it solves this problem as to why during inflation we do not drive the Higgs into this unstable state. But it also could, if you have a coupling between the Higgs and gravity, it can also generate, in effect, a slow roll potential that would be consistent with inflation. And it's even getting better than that. In addition to that, possibly explaining inflation, there's a near massless particle called the dilaton associated with the Higgs. And people now believe that if we're coupled to gravity, if Higgs is coupled to gravity, this dilaton could actually be the source of the dark energy. It could be this additional slow, very slow roll potential that is giving rise to the repulsive force in dark energy. So this whole thing with Higgs could actually solve inflation and dark energy. And since we know the Higgs-like field exists, so a similar field that comes from the Higgs that might explain dark energy, which would be very nice because it all of a sudden would make things much nicer. And this just shows how you can get a proper potential because it's a Higgs inflation. This came from this paper that was in December of last year. So this is late-breaking stuff. This is just in December of 2013. Okay, so we're almost over. Internal inflation. So, okay, I said earlier that the consequences of inflation carry with it a potential, well, more than just a potential. It's hard to see how you can avoid it, the possibility of parallel universes. And the reason for this is that if one region is exiting inflation, it exits inflation and goes down this slow roll until you get out of the repulsive gravity force and you get the normal thing. Well, it turns out fluctuations will cause some regions to go into this slow roll mode. That is, you have this Higgs-like potential tunneling through it, and some areas are going to tunnel through it sooner than other areas. And the areas that tunnel through it sooner are going to go down the slow roll, which takes a long time, relatively long time. And the areas that haven't tunneled through it yet are going to be expanding exponentially. And so it's something like radioactive decay. So in one half-life, half the regions will still remain in this false vacuum state. And that's a state that's expanding way faster than the parts of the region that are actually going down the slow roll. And so what this implies is that the expansions, once it begins, once this initial false vacuum occurs, you're going to get it will grow forever. And this comes out of, this graph comes out of, very crude graph, it comes out of Guth's book in 1984. But so you have this region of inflation in one area, he calls it a pocket universe, exits the inflation. It gets through over that hump and you're coming down the slow roll. But other parts aren't, and the parts that aren't are growing, maybe way faster. And so so what's happened is this part is leaving, but these guys are actually still at least the same size as this guy on this, and then another level comes up, but this guy is grown also up to this guy in the same amount of time. And so what you come up with is the fact that once inflation exists, the process of leaving it in the context of fluctuations mean that it's going to go on forever, and that these pocket universes, there'll be an infinite number of them, and they're still happening. And so this is what's called the multiverse, and it's there's various other theories about how multiverses could come, but inflation looks so powerful, and we're beginning to think it's more than real. It's real. This is you can't seem to get around the fact that it's not going to exit everywhere uniformly, and as a result of that, you have an infinite number of parallel universes going on, and so this gets into this conundrum that people I mentioned. Why is everything like it is in our universe? Why? And as people have observed, modern science shows that they have a pretty good handle on what's going on in our universe, but it's more like an environmental science. It's not come from some wonderful, all-powerful theory. The standard model of particle physics has 60 elementary particles and 19 adjustable parameters. That doesn't sound like something that's all that fundamental, and it probably isn't. And it says that our universe just happens to work out so that we have what we have, and it's called the anthropic principle. But other parallel universes could could easily have the same physics, but different values for these numbers, in which case they would be totally different. For example, the Higgs field. If the Higgs field is just a little bit different than it is, everything's different. All the chemistry in our universe is all different because the masses and of these fundamental particles are different, and that's all it takes to make a mess. And so the fact is that the fact that we have an infinite number can explain why we are what we are, and because we're only one of an infinite number. This book called Martin Reed's Just Six Numbers talks about these 6 critical numbers he identifies and why are they what they are. And he points out that the multiverse from inflation can in effect solve that problem. He relates it to ice freezing. If you have an ice cube, and you look at all your different ice cubes, you'll notice the grains in the ice cubes are all different, and it's because it's chaos, a little bit of chaos theory. You're entering that, you're going through a phase transition, and if every phase transition happens just a little different, and so all ice cubes are different. Well, it's the same thing here. Leaving inflation is a phase transition. Everyone is slightly different, so everyone's going to have different numbers associated, different grains in the ice cube, if you will, and so you'll have different. The universes will have different properties, and I pretty much said that. Universe's ultimate fate. I'm going to jump over this because I think we've had enough. But it looks like in 10 to the 99th years, even black holes will disappear, assuming that we continue down this, that dark energy continues to cause the universe to expand and expand and expand, and it does that forever, then everything is going to get cooled off, the stars are going to wink out, even black holes disappear, and there's nothing. And that's the dismal dark that I mentioned in the title of the talk. But there could be, and this isn't good news, but there could be a solution to this. The thing that's causing the universe to expand exponentially is dark energy. If dark energy isn't constant over time, but actually is changing due to a Higgs-like field, then dark energy may disappear at some point. Once dark energy is gone, gravity is going to take over and it's going to crunch things. So stay tuned. Stay tuned. So this is a quick summary. This is one of my pictures, by the way. That's the. This is the God. This is the Eye of God nebula, and it's a planetary nebula. That's the remainder of a star, and this is what's left of it, and it expands way big. Anyway, this one is called the Eye of God. Anyway, so the Big Bang sort of summary explains the expansion of the universe, the existence of the CMB, and the amount of light elements that exist. Data shows that the universe is flat. We now know that there's 68.9% is something called dark energy. Maybe we have some idea what it's all about. If we don't, dark matter is 26%, and the rest of everything is 4%. Based on this, we think that the universe may expand forever. A quantum fluctuation may be the origin of everything. This one little bit of false vacuum could have started not just our universe, but an infinite number of universes. And inflation also solves the issue about the uniformity of the universe, the origin, the structure, and the flatness and horizon problems. Planck has refined the Big Bang model substantially, and the implications of inflation are that we have an infinite number possible. Pretty much, multiverse looks pretty hard to avoid. We may be metastable because of the metastable nature of the Higgs field, but it also could be the source of inflation and dark energy. And over trillions of years, our 30 galaxies that are in our local cluster are going to form one megagalaxy. Other galaxies will recede from sight, and all evidence of the origin of the universe will be gone. So I'm going to end this with just some pictures. And these are in the, so I encourage you all, on Thursday at 5 o'clock, there's going to be a reception at the library, and I'm going to do a walk around of my exhibit. And then I'm going to give a talk about the, not this topic, but about astrophotography. And these are just some of the pictures that are in it. That's the Bogey Galaxy, which I just took this winter. Oh yeah, and I just took this winter. This is the Lovejoy Comet. I just caught it this night, where in some nights the tail isn't as interesting, but this night the tail was really something. The Bogey Galaxy. This is Messier 33. This is the Pinwheel Galaxy, one of the two Pinwheel galaxies. But this is in our local group. This is timely. This is the Orion Nebula, this very center part of the Orion Nebula. The part, if you look through a telescope, you see this part. There's the trapezium, and these are the thin, wispy clouds that you see through. But now I'm showing them in color because, in fact, it's hydrogen and oxygen. Hydrogen is the red, and oxygen is the blue. But your eye can't see that when you look through a telescope. This is summer. This is the Lagoon Nebula, and again, all of these pictures are in the library. This is the Pac-Man, and it's very interesting, very almost three-dimensional. This is one. I just took this. I just finished this. This is not in the exhibit. It won't be in the exhibit. But this is the famous Whirlpool Galaxy. This is two galaxies interacting, and it's this is about 25 million light years away. So this is not in our local group. This is the elephant trunk, and I've taken a picture of this through my 6-inch. And it's, that big, but it's kind of fun to take the picture with the 20-inch telescope and just looking at the very center. There's just a lot more detail. And this one is the center of the Rosette Nebula. And I've taken a picture of it with my 6-inch, but this is the very center of the through the 20-inch, and it's just a really interesting. These stars here, the solar wind from these stars have blown a hole through the gas. Have caused the dust to be pushed away and the gas to be pushed away, and it leaves this hole right through the middle of this. So all these colors come from the different. These are narrowband images, so that the red is sulfur, and the green is like in all Hubble, green is hydrogen, and the blue is oxygen. And that's it. And then this is that neat planetary nebula. The Eye of Gods. Anyway, that's it.